All right, so like I said, today we're going to cover section 6.1, 6.2, and 6.3. This last chapter, chapter 6, is about what we're going to call systems of equations. So systems of equations considers two or more equations at the same time. So we're going to have, and in fact, the only ones we're going to mess with, we'll do two variable equations. And then one of the sections is three variable equations. We won't do anything bigger than that. It is possible. You can solve, even using some of these same methods, you can solve 4 variable systems, even 5 variable 5 equations. You can go crazy. We're not going to do anything bigger than a 3 variable 3 equation system. 6.1 is all about 2 variable linear systems. So we're going to be dealing with 2 variable linear equations. So just, oops, just kicked the table and shook it. So just X's and Y's, no X squareds, no curved graphs. All of our graphs are going to be straight line type graphs. So 6.1 is dealing with 2 variable linear systems. Now, basically what this chapter is a bunch of different ways to solve the systems. So the problems aren't going to change. They're going to ask you to solve it in a couple of different ways. I'm going to say ultimately, I don't care which method you choose, as long as you are able to solve. So I'm going to give you examples of all of the different ways to solve. But when it comes down to it, you're just going to need to be able to solve. So if one of these makes more sense than the other, then do it that way. Okay, I'm going to show you all of the different methods, but I'm not going to force you to do one or the other. And I'll even show you on my math lab, it'll say solve this one by substitution or solve this one by elimination. I don't care how, you just need to be able to eventually get there. So first off, I want to talk about one of the methods for solving. This is the easiest one to understand, but it's actually the most inefficient way to go about solving it. But you can solve a 2 variable linear system by graphing. Okay, and again, the steps are really easy. You simply graph both lines and then see where they cross. And that's it. Now, seems simple. Some people are not really great at graphing. Others are really good at graphing. If you use Desmos, oh my goodness, graphing is super ridiculously easy, but you can't use Desmos on the test. I will use Desmos to show you how to graph, and it's also a great way to check your answers. So if you try testing, if you try solving by elimination, you just want to see if you got the right answer before you go plugging it into my math lab, you can go straight to Desmos, type it in, and I'll show you how to do that too. But anyway, so to graph a system. So I'll give you an example problem and we'll actually walk through solving by graphing. All right, so this is my system. So there's going to be 2 equations. Each equation has 2 variables. Since you just have a y and an x, these will make a straight line when you graph them. Okay, so x minus y equals 5 is one set of solutions. 2x plus y equals 1 will give you a completely different set of solutions. And then the solution to the system is where they cross. So for example, we do a rough sketch of the graph, so we can kind of match these up. I'm going to do this one in red here. So I'm going to graph x minus y equals 5. Now, when it comes to graphing, there are a couple of different ways to do this. You can just find individual points that will work. You can find your x and your y intercepts. You can find slope-intercept form. Most people remember slope-intercept form, so I'm going to do it that way. Okay, so for example, if we want to get y by itself, I'm going to subtract x. So negative y is going to equal negative x plus 5. And then if I divide everything by negative 1, y equals 1x minus 5. Now, when you have the y by itself, we get y equals mx plus b. This negative 5 is my y-intercept. My slope is 1, so rise 1, run 1. Okay, so that line represents every solution to that x minus y equals 5. So even the little decimal points in between where the dots are. So all of these dots work. So 0, negative 5, 1, negative 4, 2, negative 3. Okay, each of those represent a valid solution as well as the ones past. So 6, 1, 7, 2. Anyway, each of those points, and I'll actually, this whole line represents all of the solutions for this x minus y equals 5. We can play the same game, do this 2x plus y equals 1. Again, I'm going to get the y by itself. I want to put this into slope-intercept form. So if I subtract 2x from both sides, I get y equals negative 2x plus 1. So again, my b is my y-intercept, so that's 1. My m is my slope. Slope is rise over run, so I'm going to rise negative 2, run 1, rise negative 2, run 1. Okay, and then this green line represents all of the solutions for that equation. So what we're looking for is what solutions work for both this red equation and this green equation. So the green is obviously all of these. Okay, red is all of these. So there's only one point that's going to work for both lines, and it's that point of intersection. So where those lines cross is your solution. That is the point that's going to work for both of these equations. So if we look at where this point here is, it's at 1, 2, yeah, and then negative 3. This is easier to do with graph paper and straight lines, so that's why it took me a little bit. I just wanted to make sure I was on the right point. Okay, so this point here, 2, negative 3, is the solution to the system. Because if I plug my x and my y into either of these original equations, you're going to get a valid solution. Okay, any of these other points in space, like anything not on the lines, will not work for either. Anything on the red line only works for the red. Anything on the green line only works for the green. So the only one point that works for both at the same time is this point of intersection. So that's what we're looking for. And if you want to check, I can plug it into that top equation. So if my x is 2 and my y is negative 3, 2 minus negative 3 is 5, just like it's supposed to be. Same if I plug in my x, 2 times x plus y. 2 times 2 is 4. 4 minus 3 is 1, just like it is supposed to be. It checks out in that equation too. So as long as you graph them both correctly, you should get the correct solution where the two lines cross. When we write the solution, we're going to write it as an ordered pair, okay? Your solution is a coordinate. We're looking for the coordinate where those two lines cross. So we need to write our solution as a coordinate. Okay, save this example because we're going to solve this exact same equation using a couple of different methods, but I just want to talk about your solutions just a little bit. So when it comes to solving a linear system, again, if we graph our lines, one of three situations is going to happen. Okay, just like we showed, you're going to get to lines, and probably what's going to happen is those two lines are going to cross. If those two lines cross, that point of intersection is your solution. So you're going to get an X and Y solution at that point of intersection. There's only going to be one solution. You're not going to have a line that's going to cross more than once. If they're straight lines, you're only going to get one solution. This is what's going to be what happens most of the time. Another possible situation is you could get two parallel lines. They're going to run right next to each other. They're going to go up and down at the same rate and over at the same rate. They are not going to cross ever. As this one goes down and away, this one's going to go at the exact same rate. They're never getting closer or further apart. They're always going to run just side by side. They will never cross. This particular system is said to be inconsistent. There is no solution. Or some people will say that the solution is undefined. Okay. All of those go to say that there are no X and Y coordinates that will work for both lines. And again, we will refer to this system as inconsistent. When there's no solution, we say the system is inconsistent. So technically that makes this system consistent. So if this is the system that is inconsistent, then technically both of these are going to be consistent. That's one of the questions they ask on my math lab. So just be aware of that. If the lines are parallel, this is the only solution that is inconsistent. This one is technically considered consistent. Okay, a third situation that could happen is you could end up with both of your equations actually being the exact same line stacked on top of each other. Okay, this is referred to as a dependent system. Technically, this one is consistent as well, but this one is considered to be dependent. So this one would be considered independent. So if the lines never cross, you get no solutions. If the lines are stacked up on top of each other, every single point on this line is a solution for both lines. Here you get an infinite number of solutions. And then your solution is whatever the equation is, because this is represented by an equation. So if we said this is the line y equals negative 2/3 x plus 2. It's kind of what this looks like. Looks like we've got a y-intercept of about 2, slope of negative 2/3. Anyway, so your solution would be the equation for the lines. Any point that works for this equation is a point that's going to work for the system. Most of the time, this is what you're going to get. You're going to find where the lines cross, and you're going to get an X and Y solution. Just every once in a while, they're going to throw a problem at you that will either be inconsistent or dependent. And I'll show you what that'll look like depending on how we solve. Okay, so graphing is the easiest to understand. It's the easiest to see kind of what's going on, kind of see what we're looking for. However, this is an inefficient way to solve for a couple of reasons. Number one, it requires graphing, okay, either using a graphing utility or having graph paper. As you can see with my lines, when you try to sketch stuff, if your lines are not straight or if your increments aren't consistent, your lines can look really wonky, and trying to figure out exactly where they cross kind of gets difficult. Or if you don't get pretty little whole number answers. So again, I'm going to do some fictitious graph paper here. Okay. Here's my graph paper. If my lines cross somewhere in between points where it's not directly on a point. So if I kind of zoom that in a little bit, I just picked a spot inside of one of the boxes. Okay. At that point, it kind of becomes a guessing game, and trying to figure out just how accurate we need to be is really problematic. Now, again, if we're using Desmos, we can highlight over this and we can get close to within 1,000th of a point. Okay, but if we're trying to graph these by hand and we end up with some arbitrary point in between these, then it becomes a guessing game. Okay, is this 2.5 or is this 2.35? Okay, it gets a little wonky. Okay, so solving by graphing, while effective, it's also not always accurate. So we're going to go over some algebraic methods for solving. Okay, these are actually methods that I prefer, just because number one, they're kind of step-by-step, user-friendly, and they will solve even if you get like a fraction answer or something like that. So we're going to go back to the first problem we solved. So x minus y equals 5, and 2x plus y equals 1. So this is the same, there we go. This is the same problem that we solved by graphing. X minus y equals 5, 2x plus y equals 1. So we should still get this same solution. We're just going to do it using a different method. Okay. We're going to solve this one by a method called elimination. Sometimes this is called the addition method. In high school, the way we teach it now is by calling it elimination. Your book calls it elimination. So that's the proper terminology. But back in the day, whenever I learned how to solve this, 1,000,000 to 2 years ago, back in caveman days, it was called addition. So it's roughly the same thing. I'm going to write down kind of the list of the steps, and then I'm going to walk you through what it looks like when solving a problem. To solve by elimination, okay, you can multiply your equations to get opposites. That's the key. We're looking for opposites. In math, okay, opposites are positive and negative of the same number and variable. For example, 2x and negative 2x, or 4y and negative 4y, or 5z and negative 5z. Okay, you don't have to multiply your equations, but you can. That's how we're going to get them. You can multiply one equation, you can multiply both, but you're trying to get opposites. So again, same number and variable, just one will have a different sign, like 3x and negative 3x. Okay, that is an example of opposites. That's what we're looking for. Once you have your opposites, you're going to add the two new equations. And again, what should happen is one of your variables is going to drop out. We want opposites because if you add opposites together, 3x and negative 3x is 0. It's going to go away. So we're theoretically going to knock out one of our variables. So we'll be able to solve for the remaining variable. Then we're going to plug that answer back into one of the original equations. and solve for the final variable. And then if you want to, you can check your solution. Okay, so there's kind of a step-by-step method for solving by elimination. And some of these steps, like you can do multiples at the same time. Okay, like I said, whenever I walk through this, it's going to be a lot more straightforward. This is just kind of a user-friendly list of like a checklist to kind of go through to make sure you're doing everything right. Okay, step one, we're looking for opposites. Then we're going to add our equations together. We're going to solve, plug that back in and solve for the other variable, and then check your solution if you want to. Now, sometimes you're going to be lucky. And in this case, look, we've already got opposites. If you look at negative y and positive y, those are already opposites. Remember, if you don't have a number in front, it's a 1. So we've got a positive 1y and a negative 1y. So we don't need to do any multiplication. We already have our opposites. So if we add these equations together, 1x plus 2x is 3x. Negative 1y plus 1y is 0y, so that's gone. 5 plus 1 is 6. Now all we have is one variable left to solve for. Easy peasy, divide, divide. So x is going to equal 6 divided by 3, or 2. Now, one thing I want to point out. In algebra, typically you're solving for x. Just about everything we've done has been solving for x. And a lot of people will stop once they figure out what x is. Like, I know x is 2. Got it. Okay, remember, that's great, but we're trying to find a coordinate. Okay, my solution is going to be an x and a y coordinate. So I'm halfway there. I know what my x is, but I still got to figure out y. So once I know what x is, I'm going to plug that number back into one of these original equations. Doesn't matter which one. I'm going to pick the top one, so that x minus y equals 5. And I'm going to plug my x in. I know x is 2, so 2 minus y is 5. And then I'm going to solve. Subtract 2. Negative y equals 3. So divide by negative 1. And y is negative 3. So again, x is 2, y is negative 3. My solution is the coordinate 2, negative 3, which is exactly what we got whenever we did the graphing. Same system, same solution, just a different method. Okay. And again, this method is the one that most people tend to do. It's kind of the most straightforward. I will show you the other two methods. Really, we'll just talk about one within this section, but 6.3 talks about a whole nother way of solving that's really out of the box. Okay. This is the method that most people will attach themselves to. This is kind of the one that's the easiest to keep straight and to make the least amount of mistakes. And I'm going to do this example, or actually I'll do this method with a couple of other examples, but I want to show you the other method first using the same system. Then we'll do some other systems. So again, 1x minus 1y equals 5, 2x plus y equals 1. So same problem. We're just now going to solve by another method called substitution. And again, this is really just to make you aware of all of the different ways so you can choose. I don't care which way you solve. You can solve whichever the heck way you want. Even if it says solve this one by graphing or solve this one by substitution, you just need to be able to find the solution. I don't care what method you choose. I'm going to do the same thing. I'm going to kind of walk through the step-by-steps of how to solve. So substitution is you want to use algebra to get a variable by itself. Okay. Doesn't matter which one. And in a system, you've got two X's and you've got two Y's to choose from, typically. So you're just trying to get one of those variables by itself. And here's the trick. You're going to substitute for that variable into the other equation. This will make more sense again when I walk through the problem. Okay, but you're going to get a variable by itself, and you're going to substitute into the other equation. What that's going to do is that's going to give you a one variable equation to solve, which we will do. From there, it's kind of the same game. Once you know what X or Y is, you're going to plug that back in to one of the original equations. And then you're going to solve for the other variable. And then if you want to, you can check your solution. All right, so walking through this system by substitution. So we've got to get one of these variables by itself. Normally I would ask out loud and have somebody pick one, but just for the sake of argument here, I'm going to go ahead and pick one. I'm going to get this first X here by itself. So if I want to get X by itself, I'm going to add my Y over to the other side. So X is going to equal 5 plus Y. All I did was take this equation, then I want to get this negative Y to the other side, so I added a Y to both sides. So this is that same first equation, just now I have X by itself. So now I'm going to take the other equation, so that 2X plus 1Y equals 1. But I'm going to substitute instead of using the letter X, okay, because I know what X equals, I'm going to substitute. So instead of 2X, I know X is 5 plus Y. I'm going to substitute that 5 plus Y. So again, what that does is that gives me an equation with one variable now. I've got just Y's to deal with. So algebraically, I can solve. 2 times 5 is 10. 2 times Y is 2Y. Combine my like terms. 2Y plus 1Y is 3Y. Subtract my 10. 3Y equals -9. Divide. Y is -3. Okay, again, at that point, I'm going to plug this back into one of my original equations. Does not matter which one, just pick one. Done the top one a couple of times, I'm going to pick the bottom one. So this 2X plus Y equals 1. I'm going to take 2X. I'm going to plug in my Y. My Y value was -3. And then I solve. So again, add 3 to both sides. 2X equals 4. Divide. X is 2. And again, we get the same solution. We got that 2, -3. And again, I don't care which method you choose. If graphing makes the most sense and you want to graph it, you have the graph paper, great. Okay, if you want to solve by elimination, awesome. If you want to solve by substitution, wonderful. I don't care, it doesn't matter to me. Okay, also, as a reminder, I'll share my screen here. We go into Desmos. This is a great way to check your answer. If you don't want to plug it in, now remember you can't use Desmos on the test, but when it comes to your homework, if you just want to use Desmos to check, you can simply type in your equation. So X minus Y equals 5. And my other equation was 2X plus y equals 1. You can clearly see my lines cross. If I click here, it highlights and says, oh, look, you cross at the point 2, -3. So you can use that to check your solution as well. So you have a digital way to verify that your answer is what it's supposed to be. And the good thing about using Desmos is you don't have to manipulate your equations. You can type them in pretty much exactly the way they look. Just put them in 2 different boxes. It'll graph both lines, look for where they cross. All right, so like I said, most people, when it comes to solving, will attach to one method or the other. A lot of people like that elimination. I'm going to show a couple more examples of it. Like I said, to me, it seems the most straightforward, but we'll do a couple other problems. So this is going to be a new system. So let's say we got 3x plus 2y equals -5. Come on, zoom in. Focus. There we are. 3x plus 2y equals -5. And then x minus 4y equals 3. So again, I've got 2 equations. I've got a 2 variable system. This is probably going to be 2 lines that are going to cross. We're looking for that point of intersection. I'm going to solve this one by elimination. You could very easily solve it by graphing or substitution if you want. I'm going to do elimination. All right. Again, if you don't see a number in front of one of the variables, it's a 1. The last system, we were automatically given opposites, my positive y and my negative y. In this case, we are not given opposites. So we've got a 3x and a 1x. We've got a 2y and a -4y. So we're going to have to do something. We're going to have to multiply one or both of these equations by something to get opposites. The easiest way to do this, in my mind, is to decide whether you want to cancel out your x's or your y's. Okay, just for ease, I'm going to cancel out my x's. You could just as easily cancel out y's. I'm going to cancel out x. So the way I look at this is, here I've got a positive 3x. The opposite is a negative 3x. So how can I make this one a -3? I'm going to multiply it by a -3. And when I do that, I can't just multiply it to the 1. That would change my equation. So to make sure I don't change the whole thing, I've got to multiply that to every number. So I'm just going to rewrite that top equation. So 3x plus 2y equals -5. And again, to get my opposites, I need to multiply this 1 by a -3. So that gives me a -3x, which gives me my opposites. That's what I'm looking for. Okay, also -3 times -4y is 12y. And then -3 times 3 is -9. So if you don't have opposites to start with, you need to multiply to get opposites. Once you have your opposites, you add your equations together. Now my x's cancel out, and I'm left with 14y equals -14 if I add those together. So 2y plus 12y is 14y. -5 plus -9 is -14. And I've got one variable left to solve for. Divide, divide. Y is -1. Now again, remember, my solution is going to be a coordinate. Right now, I just have one piece. I just have the y. I'm still looking for that x value. To get it, again, you take your variable that you know, and you're going to plug it into one of these original equations. I plug it back into the original equation. You could technically plug it in here, but because we did some math and we manipulated one of these equations, there's potential for there to be a mistake. So instead of just plugging it into one of those, I'm going to go back to the original. This is the problem I was given to start with. There's no error there. So I'm going to plug it into one of those. And it doesn't matter which one. I'm going to plug it into the bottom one because I can. So 1x minus 4y equals 3. So 1x minus 4y equals 3. And I'm just going to plug that y value in. So my y value is -1. So I'm going to put it in for the y. So 1x, -4 times -1 is +4. Subtract 4 from both sides. And x is also -1. So this coordinate, okay, is my solution. Again, really easy to check it. If we want to, we could just simply plug it into the other equation. So 3 times -1 is -3. 2 times -1 is -2. -3 and -2 is -5. It checks out. Or again, just as easy, go to Desmos. And type it in. So we got 3x plus 2y equals 5. And x minus 4y equals 3. Oop, -5. It's like something's not right. It does help if you type it in correctly. Okay. And again, it's going to graph the lines for you. You can see where they cross. They cross at the point -1, -1, which is exactly what we said it should cross at, -1, -1. So Desmos is a great tool for checking your solution, but this is again just an algebraic way to solve the system. Again, if you wanted to graph it, you could. This one doesn't graph quite as nicely just because it's tougher to get the y by itself. Also, solving by substitution, to me, it just seems like a more difficult process. Elimination is just more straightforward in my mind. That's the one that I tend to gravitate towards. All right, I want to do one more example before we move on. And occasionally they'll do this kind of thing. Okay, and they'll give you a new system, but it's going to be out of order. Okay, what I mean by out of order, the standard form for an algebraic or for a linear equation is to do your x value and then your y value, and then it's going to equal some constant. This is what we call standard form. Occasionally, they'll give you something that's out of order. Okay, to solve by elimination, we need to put this into standard form. Okay, you're going to want to get your x and your y's on the same side. You want your x's to be first. You want everything to line up nice and neat. We can't do elimination as it stands just because we don't have our like terms all lined up. So just some basic algebra manipulation. So for example, for this 4x equals y minus 3, I need to get my y to the other side. So I'm going to add the opposite. So 4x minus y is going to equal -3. So if I subtract that y to the other side, I'm going to go ahead and put my 1 in front as well. We can do the same thing here. We've already got the y. We've got our constant. We just need to move our -8x over. The opposite of subtracting 8 is to add. So we'll get 8x plus 2y equals 5. So if things are out of order, add the opposite to move stuff to the correct side. Again, you want it in standard form. You want your x's and your y's on the same side, constant on the other. Okay, from here, steps are going to be the same. Again, I'm going to solve by elimination. I want opposites. I've got a +4 and a +8. I've got a -1 and a +2. I don't have opposites, so I need to get them. And it doesn't matter which one we want to cancel out. If you want to cancel out your X's or your Y's, I'm going to cancel Y's. So that means I need to double this top equation. So if I distribute my 2, I'm going to get 8x minus 2y equals -6. So I just distributed that 2. Add my 2 equations. I get 16x. My y's cancel. 5 minus 6 is -1. And I get a gross fraction answer. So x is -1/16. Most of the time you will get pretty little whole number answers because math teachers like pretty little whole number answers. They're easy to grade. However, in real world applications, that rarely happens. So if you get a fraction answer, don't freak out. It is entirely possible to have a fraction solution. We're just going to keep going. So once we know what x is, we're going to plug it in to one of our original equations, doesn't matter which one, and we're going to solve. So I'm going to, again, choose the bottom one. So 2y equals 5 minus 8x. 2y is going to equal 5. And then -8 times a -1/16 is a +1/2. 5 plus 1/2 is 11/2. Divide by 2, y is 11/4. So most of the time you will get pretty little whole number answers. Occasionally you may end up with some sort of fraction answer, which we could still check if we wanted. All right. Real quick, I want to show you what it looks like. So obviously, if we're graphing, it's easy to see what an inconsistent system looks like. Also graphing, it's pretty easy to see what a dependent system looks like. But if we're solving by elimination, it's not quite as obvious. Now, they're usually not going to start out like this, but usually you're going to have to multiply to get your opposites. But really quickly, if you're going to solve and you go to add your equations and both your x and your y drop out, cancel, end up being opposites, but your constants do not, that's going to give you something along the lines of 0 equals 8, which is obviously not true and is therefore an inconsistent system. If we were to graph these, we would end up with 2 parallel lines that would have different y-intercepts. They are not going to cross. So this is an example of an inconsistent system. So if you are solving and both x's and y's cancel, but the constants do not, That's going to be your inconsistent system. If you are solving and everything cancels out, your x's are opposites, your y's are opposites, your constants are opposites. So whenever we go to add those equations, everything cancels out. What that means is you have the exact same equation. That means you're going to get the exact same line. Therefore, you have a dependent system. Using regular elimination, if just one of your variables cancels out, like just your x or just your y's, then you're going to be able to solve for the other variable, and you're going to therefore get a solution. But if both x and y cancel, then it's either going to be inconsistent or dependent based off of whether or not your constants cancel too. Again, if everything cancels, exact same line, dependent. If your constants do not cancel, parallel lines, inconsistent. But like I said, most of the time you're going to get a singular x and y solution. And in fact, most of the time they will be pretty little whole number answers. All right, now we get to ramp up the difficulty considerably. 6-2 does more of the same, but it adds an equation and a variable. And like I said, this also adds to the difficulty, because with a 2-variable system, you get straight line graphs, 2 variables, x and y, straight lines, flat, easy to graph. When you're dealing with a 3-variable system, you are dealing with a 3-dimensional graph. Okay, you're dealing with x and y and z. You're dealing with 3 planes. So graphing gets really, really, really difficult. We're never going to solve a 3-variable, 3-equation system by graphing. Okay, it would take a special kind of program with a special kind of software to be able to do so. We're not equipped with that. We're not. Okay, there is equipment out there that can do it, but we're not dealing with it in 3-dimensional space. So I'm going to just show you an algebraic method for solving. Okay. Now, again, I'm going to preempt this by saying it is entirely possible to get a bunch of different kinds of solutions. We're not going to deal with that. Every one of the systems we solve will end up with a pretty little x, y, z solution. So everything we're going to be doing will solve nicely. There are situations where that is not the case. That is beyond the scope of this course. So if you are given a 3-variable system, like x plus y plus z equals 2, 6x minus 4y plus 5z equals 31, and 5x plus 2y plus 2z equals 13. Okay, if you're not on a brand new piece of paper, you're going to want to be, because this takes some room to get it done. There are some steps to this. The process for solving a 3-variable, 3-equation system is basically, it's like double elimination, okay? We have to do elimination to get rid of a variable, and then we have to do elimination again to get rid of another variable. Okay, once we can solve for one, then we can start doing our plugging back in. So, very similar to elimination, which again is why I kind of focused on that one with the 2-variable systems. This is really the best way to solve a 3-variable system. Again, you want to multiply to get opposites. We're not trying to cancel a whole bunch. We just want to pick 2 of our equations. I'm going to number them so it's easy to identify. So equation 1 is referring to this top one, x, y, z, okay, and 2. Equation 2 is going to be the one here in the middle. Equation 3 is going to be this one down here at the bottom. Okay, and again, we need opposites. We need to cancel something. It doesn't matter which variable you want to get rid of, because I can. I'm going to get rid of my x's, so that's what I'm going to focus on. So I'm going to use equations 1 and 2, and again, I'm going to try and cancel my x. So again, equation 2, 6x minus 4y plus 5z is 31. To get rid of my x, I need the opposite. The opposite of 6x is a negative 6x. So to make my 1 a negative 6, I need to multiply equation 1 by negative 6. I need to distribute, so I get negative 6x. I get negative 6y. I get negative 6z equals negative 12. So I'm multiplying negative 6 to equation 1. That was this one. So I got to multiply to the x, the y, the z, and the 2. And that's going to cause my x's to cancel, which is what I want to happen. So I'm left with negative 10y, negative 1z equals 19. All right, that's step 1. Step 2, and this is the key. This is what's going to make this work. We have to choose 2 different equations. So I can't pick 1 and 2 again. I can pick 1 and 3, or I can pick 2 and 3, but I got to cancel the same variable. If I cancel a different variable, that doesn't help me out. It doesn't gain me any ground and I can't move on. So I'm going to pick 2 different equations. So I'm going to pick 1 and 3, but I want to cancel the same variable. I got to get rid of my x's. Okay. That's the only way this works. So 3 is fine. 5x plus 2y plus 2z equals 13. And again, I want to get rid of my x. So I need to make this an opposite. So I'm going to take equation 1 times negative 5 this time. So if I take negative 5 times equation 1, I get negative 5x, I get negative 5y, I get negative 5z equals negative 10. And again, I'm going to add, and my x's are going to go away. I get negative 3y minus 3z equals 3. Now, what that did is that gave me a 2-variable 2-equation system. I can take what I have now and do exactly what I just did last lesson. So now, if I bring this guy over here, I've got a negative 3y, I've got a negative 3z equals 3. And now I can solve this equation. So again, I'm looking for opposites. I'm going to cancel my z. So I'm going to multiply the top by a negative 3. So that's going to give me 30y plus 3z equals negative 19 times 3, 57. I've still got negative 3y. I've got negative 3z, 3. Add, my z's cancel. I get 27y equals negative 54. We're finally down to one variable, which I can solve. Divide, divide. Y is -2. All right, now we got to do a bunch of that back substitution. We got to plug things back in. So we had to do all of that work to solve for one variable. Remember, when it's all said and done, I need 3. I need an X, I need a Y, and I need a Z. Right now, all I know is what Y is. Y is -2. So I'm going to plug that back into one of my 2 variable equations. So if I know what Y is, I can plug it in to solve for Z in either of these equations. It doesn't matter which one. You don't want to go back to the originals because then you're having to deal with an X2. We want to deal with one of the ones where we've already gotten rid of X. It doesn't matter which one, just pick one. Since my arrow is pointing at that bottom equation, I'm going to do it. So -3 times Y, which is -2, minus 3Z equals 3. And then I'm going to solve that for Z. Just basic algebra. So I multiplied -3 times -2, subtract 6 from both sides, divide by -3, and Z is 1. Now, once I know Y and Z, now I can plug back into one of my original equations. I'm going to pick the simplest one. So that X plus Y plus Z. I don't know X, but I know Y is -2. And I know Z is 1. So now I can solve that for X. So my solution is the coordinate 3, -2, and 1. I understand that seems like a lot, but that's really the best way to go about solving an equation like this. Unless you did what I told you to do at the beginning of the semester and you bought this calculator. If you have a calculator that is this same one or very similar, it will totally do all of this for you, and you're going to be really happy that you bought it. So if you've got the Casio FX 115 ES Plus, or again, there's another Casio that's very similar that can also do this, I'm going to walk you through how to solve this using your calculator, and you're going to be really happy in about 2 seconds. Okay. All right, turn your calculator on if you have the right one. Okay, if you click mode, and it gives you choices, one of which says equations. That's choice number 5. Choice number 5 is EQN for equations. You've got the right calculator and you're in the right place. So you're going to hit choice 5. Okay, and again, it's going to give you a bunch of choices here. We want the one with an X and a Y and a Z. That's going to be choice 2. When we click on choice 2, that gives us a whole bunch of zeros. You're going to fill those zeros in with the coefficient. So you're just going to hit the number, hit equals, and it'll move you to the next one. So in this case, if you hit 1 and then you hit enter, it'll take you to the next box. You're going to hit 1 again, next box, hit 1, hit equals. Every time you hit equals, it's going to send you to the next box. You can't really see what I'm typing in. The lighting's not very good. And then I'm going to hit 2. Then I hit equals, okay, and it jumps down to the second equation, first one. So then I'm going to type in 6, and then -4, and then 5, and then 31, and then 5, and then 2, and then 2, and then 13. When it's all said and done, when you've got all your numbers entered in and you hit equals, your calculator is going to tell you Come on, play nice. Okay. It says x equals 3. So my x is 3, just like we said it was. If I hit equals again, now it says y is -2, which is what we said it was. And then if I hit equals again, it says z is 1, just like it said it was. So if you have the correct calculator, it will totally solve all of this for you and will save you having to do any of the work. Thank you, calculator. That's really nifty. Okay. So again, the steps: mode 5, 2. Then you go ahead and put in all of the numbers. Don't worry about plugging in x and y and z. You're just going to plug in your coefficients. So that would be, we're plugging in 1, 1, 1, and then the constant 2. And to jump down to the next one, we hit 6, and then -4, and then 5, and then 31, and then 5, and then 2, and then 2, and then 13. And then you hit equals, and as you scroll through your equals, it'll give you your solution. So again, when entering the numbers, every time you hit equals, it'll jump to the next one. You got to hit equals in between each number. You can practice with that, and this will totally solve those 3 variable systems for you, and that's going to save you a ton of time and work. All right, I do want to do another couple examples of that. This will at least give you a chance to play around with your calculator if you want to. If not, I want you to have some more examples to draw from when you're doing your work. All right, so we're going to do another problem here. All right. If they give you a problem that looks like it's broken or stuff is missing, okay, still very doable. Okay, all we're going to do is we're just going to put zeros for placeholders. All right, so if I just have a 2x plus z, okay, I'm just missing my y, so you can replace that with a 0. Okay, same song, different verse with the second equation here. I've got a 3y minus 2z equals 6. I'm missing my x, so that's a 0. Same song, different dance. Third equation, 1x minus 2y. So then my z is a 0. So if something is missing, just put a 0 in as a place holder. And then, like I said, if you want to try solving this using your calculator and get done faster than I'm going to do it otherwise, you can do that. Okay, I'm going to walk through the elimination method. All right, again, I want to choose 2 equations and I want to cancel a variable. Since it doesn't matter which one, okay, I'm going to choose, if I just take equation 3, look, one of my variables is already gone. Okay, z is already gone, so I don't have to worry about it. If I pick equation 3, I've got one variable eliminated. Now, the next part is what makes this work. Again, I'm going the long way through this. I've got to choose 2 different equations, but I've got to cancel the same variable. So it doesn't matter if x is gone or if y is gone in a different one. I got to get rid of z because that's what's missing here. So because z is what I canceled out, I need to choose 2 equations and I need to cancel z. So again, I'm going to choose equations 1 and 2. So equation 2 says 0x plus 3y minus 2z equals 6. And I want to get rid of my z. Since I have a 1z here, to get rid of my -2, I need this to be a 2z. So if I take 2 times equation 1, I'm going to get 4x. I'm going to get 0y. I'm going to get 2z equals 2. So now if I add those two equations together, my z's drop out, and I get 4x plus 3y equals 8. Okay, awesome. Now I can take my two variable equations and I can solve them. So I'm going to bring this one down here just because it's going to work out better. So if I take my 1x minus 2y equals -9, I want to cancel one of my variables. So again, if I've got a 4x, I want to get rid of this one. So I'm going to take the bottom equation times -4. So I'm going to get a -4x. I'm going to get a positive 8y, and I'm going to get a positive 36. So that whenever I add those together, I'm going to get 11y equals 44. Now I'm down to one variable, divide, y is 4. Now remember, I want to plug him into one of these two variable equations, doesn't matter which one. It's a little cleaner over here, so I'm going to plug it in over here. So 1x minus 2y, remember y was 4, equals -9. So x minus 8 equals -9. Add 8 to both sides. X is -1. Then I'm going to plug both of these guys into one of these equations. Doesn't matter which one, just make sure it has a z because that's what we want to solve for. So I'm going to choose the top one. So 2x plus 1, z equals 1. And z is 3. So choose two equations, cancel a variable. Choose two different equations, cancel the same variable. Solve your two variable system. Plug back in, plug back in. And again, we need to write our solution as a coordinate. It always goes in alphabetical order. So we're going to do x and then y and then z. So the x was the -1, the y was the 4, and z was 3. This is my solution. My solution is always going to be a coordinate. So even the 3 variable, 3 equation systems need to give your solution as a coordinate. All right. Again, if you have the right calculator, that's going to make that go way faster. So much easier to solve when you have the right equipment. Now, the last section really isn't super necessary. It's just another way to do the same thing, but it introduces a completely different tool. So 6.3 is an introduction to matrices. And then solving systems using the Gaussian elimination system. Okay. The introduction to matrices is kind of nice. I'm going to go ahead and show you. So a matrix is simply a rectangular arrangement of numbers. So quite literally, they're just going to take some numbers and they're going to arrange them in rows and columns. Okay, the rows go left to right. Okay, the columns go up and down. If it asks for the order of a matrix, you give the number of rows by the number of columns. This particular problem has 2 rows and 3 columns. This is an example of a 2 by 3 matrix. Okay, this is an example. We have 3 rows. We have 4 columns. This is an example of a 3 by 4 matrix. So again, that's just simply the order of the matrix. It's kind of asking for the size. Okay, we always do the number of rows first. Again, the rows are the left to right. Then we give the columns second. The columns are the up and down. So this would be an example of a 4 by 1. You would have 4 horizontal rows. You only have 1 column. Now, there is a bunch of stuff you can do with matrices. In fact, there's a whole branch of math dedicated to matrices and vectors and studying them and all the different things you can do. We're just doing a very brief introduction. In fact, today we're not doing much more than talking about the order. And then I'm going to show you how to augment a system into a matrix. For example, if they gave you this system, we can write what is called an augmented matrix. And it's kind of what we did. If you paid attention to how you typed the system into your calculator to solve it, okay, when it gave you all those zeros, it was giving you an augmented matrix and you were entering the numbers in. So same thing. So you just enter in, so 3x, we just enter in the 3. This 1y, we would enter the 1. For the 2, we enter the 2. So it's just rewriting the system. This is called augmented. It's just simply rewriting the system without the variables in order and converting it into a matrix. So 3x plus y equals 2 is 3, 1, 2. 2x minus y equals 4 is 2, negative 1, 4. This is again what we call augmenting or making an augmented matrix. You can do the same thing for a 3-variable system. Again, you basically just drop the variables. So 2x plus 1y plus 1z equals 3 would be 2, 1, 1, 3. 4x minus 1y minus 1z equals 1 would be 4, negative 1, negative 1, 1. Again, if some term is missing, you need to put a 0 in as a placeholder. So this is 2 x's and then 0 y's and then 1 z equals 1. So again, when you augment it, everything needs to be in order. They should give you the equations in order. It should be x, y, z, okay, or just x, y. But when you augment it, we do the x's with no x's, we do the y's with no y's, and then we do the constants. So again, this is just what we call writing an augmented matrix. Now, okay, just trust me on this. You're going to want to follow along, but don't pay a lot of attention because this is another way to solve a system, but oh goodness, this is not the easiest way to go about doing this. All right. We're going to take a 2-variable linear system, and we're going to solve by what they call Gaussian elimination. So just kind of follow along with me. My math lab is going to tell you to solve using this method. I would not solve using this method. I would solve using any one of the other methods we talked about. I would graph or do elimination or do substitution or do the cool kid calculator. Okay. This is not the method I would choose, but I will walk you through how to do it just so you have been exposed to it. So step 1 is to write an augmented matrix. Then we're going to do what's called matrix row operations or Gaussian elimination in order to get this picture. Okay, you want a 1 in the top left, you want a 0 in the bottom left, and you want a 1 in the middle bottom. Because that's going to help us to generate our solution. Again, just kind of play along with me. With matrix row operations, there's only a couple of things you can do. You can swap rows, you can distribute a number, or you can add rows together. Those are the only 3 things you can do while maintaining the equality of the rows. So what we're going to do to get a 1 here in the top left, we've already got it. So I'm just simply going to keep row 1. Next, I want to get a 0 here in the bottom left. So I'm going to take, the only way I can get rid of this 2, okay, I can't multiply by 0 because that's going to cancel everything out. So I've got to multiply by some number and then add my rows together. So if I take -2 times row 1 plus row 2, I'm going to get what I want. So -2 times row 1 is a -2. Okay, plus row 2, so -2 plus 2 makes this number a 0. We'll keep going. So -2 times -4 is 8, plus row 2, so 8 plus 5 is 13. And then -2 times 9 is -18, plus row 2, so plus 5 is a -13. So I was lucky enough to have my 1. I had to do my matrix row operations to get my 0. Next, I want to get a 1 here without changing my 0. So I don't want to multiply and add because that's going to change my 0. So all I'm going to do is I'm going to take row 2 and I'm going to multiply by 1/13, or I'm going to divide by 13. So 0 divided by 13 is 0. 13 divided by 13 is 1. -13 divided by 13 is -1. And then if I keep row 1 the same, I have the picture I'm looking for. Now, the reason we want that picture and how this works, if we unaugment, okay, then what we have is x minus 4y equals 9. But then this bottom equation says y equals -1. So that basically solved for one of the variables. And then if I plug him in, x minus 4 times -1 is 9. I can get my x. X is 5. So my solution is the 0.5, -1. Until you have practiced this, this is a very convoluted way to go about solving. And especially when you start doing like 3 variable, 3 equation systems in this method, it will eventually get you there. But man, some of the problems you're dealing with get really ugly. Okay. It is 100% doable. It is not the method that I would recommend. To me, elimination is far more regular elimination, not Gaussian. Regular elimination is a lot more straightforward. And again, for the scope of this course, you just need to be able to solve. If you would like to use Gaussian elimination, that is more than fine. It is not what I would recommend. Okay. If you're going to pursue mathematics and you're going to be taking linear algebra, you're going to need to learn how to do matrix row operations. If that is not your career path, then not worth messing with. This is, again, this is kind of one of those, I don't want to say tricks, but it's kind of one of those things that people that are really good at math like to show that we can solve methods in a bunch of different ways. And this is just another way that works. So I would solve this using a different method. To me, elimination would be a far more straightforward, easy way to solve. Or the cool kid calculator will solve 2 variable equations just as easily as 3 variable. It's kind of the same button pushes. It's mode 5, 1. So instead of mode 5, 2, it's mode 5, 1. And again, you enter your augmented matrix in here. So 1, -4, 9, 2, 5, 5. And again, I hit equals. It says that x is 5, like it was. I hit equals again. It says y is -1, which it was. So again, if you have a calculator that can solve systems, this is a great way to solve the system. This is something you can use on a quiz or test. Now, you can still use Desmos to check all of your stuff. Desmos doesn't work with the 3 variable systems. So with those, you take your time, don't make silly mistakes. Basically, that's what I got for you. If you want to stick around and ask questions, you can, but that covers 6, 1, 2, and 3. Again, I'll be uploading this video for the people that were gone. Anyway, that's what I got. Next Thursday, we will finish up. This is going to be the last 2 sections. We're going to cover 6, 4, and 6, 7. That'll be it. The following Thursday, we test over systems. The following Thursday, we take our final, and that's it. So again, it'll be the week before finals week. So make sure you're paying attention to those dates on that matrix I gave you. Other than that, you guys are free to go. Again, if you have any questions, I'll be here. So if you have questions, ask them. Otherwise, I'll see you next Thursday.
Have a good night.
See ya.
See ya.